Okay, can you guys see the screen?
Yes, sir.
Okay. Just 1 second, I open this. So let me go over this quickly. In the last class, we looked at this framework of Markov decision process. Essentially, the idea was the states and actions are evolving in some Markovian fashion, and there is a reward attached to each state, right? An action that you take. So we looked at what is known as an infinite horizon problem, meaning you look at the discounted average of the rewards that you get over time. You look at the average conditioned on some initial state S. So we basically proved that I can write this the reward or the value that you get as a consequence of you taking policy pi is given by this expression, right? R pi, that is the reward that you get when you are in pi, that's the vector, plus nu, that is the discount factor, p pi, that is the transition probability matrix when you take policy pi, times v pi again. Okay, so this is the iteration that we got. In fact, this is called so a slight variant of this is called a um, um, Bellman equation. That's what we will look at today. Okay, is that fine? Everything fine, right? Okay. So subsequently, we also saw when we can find v pi, right? That is, v pi is this I minus nu times p pi inverse r pi. So essentially, whenever this matrix inversion or the operator inverse exists, then we can find v pi through this inversion. So in fact, in the last class, we showed that the inverse exists in this case, and therefore you can find the value through this equation. Okay, so that's where we were. So now let's start. Okay, let's see what happened. Okay. Okay, yeah, good. Okay, let's get started. Lecture 36. So in today's class, we will continue with the value and introduce a few algorithms, at least one called value iteration. So first of all, let's look at. So you have this v pi of s, right? What is this? Can somebody tell me? What is v pi of s? This is the average reward that you get if you start from some state S and follow a policy pi, right? That's what it means, right?
Yes.
In fact, what is it that I want to do? I want to find, so the problem is the following, right? So I want to find the policy. That means I want to find a pi star, which is nothing but arg max of this v pi of S, right? So this is, let me call this as pi star. You maximize overall policy pi, right? You take different policies and you will see what is the value that you get for when you start from some state S, and let me call that as pi star. In fact, strictly speaking, I should call it as some pi star subscript S or something, because it depends on what S is. Anyway, so I'll just not write that, and the corresponding value, I will write it like this: v star of S, because it depends on the status. Is that fine? So essentially the problem of MDP boils down to finding this policy pi star. That's all. Okay. Now towards that, let's see a few more things. So for example, I'll just write this in a pictorial fashion. Suppose I'm in some state. Let's look at the Viterbi sort of algorithm, right? So suppose I'm in state T. Okay. Now T minus 1, let's say there are 3 possible states that you can be in. Okay. Now from so sorry, let's look at the other way. I'm sorry, not the terminal. Let's start with the initial. Okay. Suppose you start in some state. This is the initial state. Okay. T equal to 0, and you are in, let's say, T equal to 1. You can be in 3 possible states. Okay. This is T equal to 1. Now what can happen is if you start in state S, suppose this is state S, you start here. Okay. Now I might go to this state. Let's say this is state 1, state 2, state 3. Okay. Again same state 1, state 2, state 3. Right. I can go from state 2 to state 1. There is a probability associated with it, which is nothing but the probability of you being in state 1 given that you are in state 2 and you take an action here. Right. Or I can go to state 2, there is some probability associated with it, or I can go to state 3. Now if you are in state 1, right, I can follow certain policy and you get the best possible reward after from state 1 at time 1. Okay. And similarly state 2, you can follow the optimal policy and you end up with a certain reward here. Okay, that's the best reward that you can achieve, assuming that you are in state 2. And similarly state 3 is, let's say, like this. Okay. Now what is this? This is basically the best possible that you can have when you start at state 1. Right. What is this? This is the best possible that you can have when you start in state 2. This is best possible when you start in state 3. Right. This is a time step 2. Well, if you look at the long term behavior, it doesn't matter, right? One step does not matter. So now what is the best that I can do from here? Well, I can take an action that will I'll end up in state 1 and I get a reward, and subsequently I get something, and so on, right? So that's what I will end up getting. So let me write expression related to this. So suppose I end up in state S dash. Okay. So V star of S dash is the value or the discounted reward that you get subsequent to this state S dash. So after S dash, you are going to take optimal actions or optimal policy you'll follow, and you will get this is the reward, right? Suppose to begin with you are in state S and there is some chance of you reaching S dash, right? So that chance is what? Probability that you will end up in S dash given that you are in S and you take an action A. Right? Suppose you take an action here when you are in S, you end up in S dash, and subsequent to that, this is the action. But this S dash can be anything, right? So I can take overall S dash. That gives me the average best reward that I can get if I start from state S and take an action A, right? Now let me multiply the discount factor and let's add the reward that I get of taking action, being in state S, taking action A, the average. Okay. So
Hello,
let
sir.
me, yes.
Sir, I was summing on S dash. Sir, why we not considering actions also, like actions? They are different. So when we are averaging, like we are considering only S dash over S dash. So A is also variable, like for every state, different
No,
actions.
A is what? So suppose I give you a, so there are two ways to look at A, right? I can take an action directly, or for a given policy will tell me what action to take when you are in S, right? For example, if you are looking at it in terms of policy, this can be pi of S, right? If you are in state S, you take a policy pi and that will maximize. But the problem is the best policy here is some pi star that you have followed, right? I could have as well used the same policy here, right?
Yes,
You
sir.
agree? So,
Yes.
and similarly here, right? But I want to look at what is the immediate action that I should take that maximizes the entire thing, right?
Okay, sir.
Okay.
Yeah.
Okay. So
Yes, sir.
yes.
Sir, me being in S dash is a consequence of taking action A, right?
Me being in S dash is a
Yes,
consequence of you being in state S and taking an action A.
yes.
That pushed you to state S dash with certain probability. Okay.
Then going to S dash depends on A, right?
Depends on both S and A, right?
Yeah, both S and A.
Yes. Yes. Okay. Okay. Is this fine? So now, well, if you look at the value, the previous, if you go back to, if you recollect, so we had written this V pi of S also, right? What is V pi of S? It is expected value of R of S. When you take a policy pi, that means pi of S is the action, plus nu times summation S dash, probability of S dash given SA, V of or V pi of S dash. Right? What is the difference? The entire V pi is written in terms of the policy pi, and you have to optimize overall policy pi, right? That's the entire, it will describe the entire path. Whereas here, I kind of figured out what happens after S dash, the best possible thing. But in order to reach S dash, I may have to take certain action, right? What is the best action that I have to take so that I reach that S dash, which results in maximum, overall maximum, right? In fact, V star of S dash could also be large. Is this fine? So you see the difference between the this V pi and the Q function. This is the state action value function. Okay, state action. Don't worry about the terminologies.
Sir, is it that like, sir?
Yes, yes, yes. Go ahead. Yes,
Hello.
yes.
So like, is it that basically maximum reward which we can get from Q star in SA by taking any action, that will be equivalent to V pi of S?
Can you repeat that? Sorry, I missed the point in between.
So, can we write V pi? So can we write V pi S equal to maximize over all the Q star SA overall action?
No. So okay, let me write it in a slightly different fashion. So for example, you take, so what is V pi of S?
Okay.
If you are starting from state S, and if I follow a policy pi, this is the average discounted reward that you get, right? What should I do? The problem is to maximize overall policy pi, right? What will this give us? This gives us V star of S, right? Do you agree? Do you agree? Who was this? Sorry. Mandeep, do you agree? Do you agree
Yes.
with this? Right?
Yes, yes.
Now, what is Q star of SA? It says you are in state S and you take an action A, right? As a consequence of you will end up in some state with certain probabilities, right? But subsequent to that, you will take optimal actions. Then what is the average reward, right? Now, think of a situation where you have to take an immediate action, but subsequent to that, there is some, let's say God will tell you what is the optimal action. You take that and you will maximize, right? So now, if I maximize overall action A, these two will be equal. Do you agree?
Yes, it's, yeah.
Okay, sir.
Okay.
Like,
Because, yeah.
two curves intersecting in that point, kind of. One maximize over A or plot over A and against A.
Yeah,
and
so this is A is like the immediate action that you are going to take. V pi is the policy that you have to take. So this is a difficult problem, right? V pi, because you have to tell what is the function which maps states to action that you have to choose that maximizes V pi of S. Whereas here you have to just tell what is the action, right? A. If there are 3 actions possible and there are 10 states, the second problem, that is this problem, there will be how many? So each one there are 10 states, 10 power 3, right? So 1000 possible functions are there. You have to optimize over that. Whereas here you have only 3 actions, so you have to optimize over 3, right? It's a relatively easy problem. But of course, hidden in Q star there is V star. But the question is, how do you find V star, right? Okay. So now what is V star of S? I'll just write this and get back to you. Is that okay? Just I'll finish this.
Okay, sir.
Maximize your all action. Expected value of R comma R of S comma A plus the discount factor summation overall S dash belonging to S, probability of S dash given S comma A times the V star of S dash. Okay, so this is what we have. Yes, go ahead, Sumit.
Yes, sir. In the queue, sir, just scroll it down, sir, a little. In the
Just
queue,
one
sir.
second. Okay,
In
yeah.
in the queue, sir, you have taken the summation over S, and this A is here the optimal action, no, sir? In the queue,
No.
S, a Q star
This,
S, a, sir.
this is any action here.
No, sir, in this summation,
Suppose,
under the summation, the probability of S dash,
no. This
condition
is
of.
also this A and this A are same. Okay.
So, sir,
See,
this
if there are
action has
three,
to be the optimal action at the position S, so that we can get the, sir, V star of S dash, right, sir?
exactly, yeah.
So, A
One
is
step
here
action should be best.
yeah. Means, sir, I am saying that this action is the optimal action at the stage S, sir, right?
Yes.
Okay, sir. Okay.
Yeah. Okay.
Yes, sir.
Okay. Is that fine? Yeah.
Yes, sir. Yeah.
See, it's like this. Okay. So, immediate. So, if you look at the immediate reward, right? For example, you being here and taking action 1 versus 2. The immediate reward could be, for example, action 2's reward could be very high. But subsequent to that, the overall reward could be very low. So that you will end up taking action 1 despite the immediate reward being small, because it leads to a state which subsequently will result in a big reward on an average. Okay.
Yes, sir. Yeah. So
That's
it
the
means, sir,
idea.
it will give the better result, I think. No, sir. Instead of following the policy, sir, because one
No,
policy after
there's
some stages
nothing like that.
may.
So essentially, either you have to solve this problem or this problem. It doesn't matter.
Oh, this is
Okay.
also we are maximizing. Yes, sir. Yeah.
Yeah. So whichever results in a better, whichever you have a better handle on, which can lead to good algorithms, that's what you choose.
Yes, sir. Yeah. Fine.
Okay. Yeah. So now let me rewrite this in a slightly different fashion. Okay. So what is this guy, this particular expression doing? Okay. So now I can think of this in a slightly different, different fashion. Okay. So for example, maybe I'll write this in a, or I can also write, for example, the previous one, right? If you just look at V of S, right? And then subsequently I can, okay, so let me write a slightly different way. Okay, so I'll write it like this: max overall A, okay, expected value of R of S comma A, okay, plus new times S dash belonging to S, this conditional probability, okay, and I will so I'll write it as V of S dash. Okay, I'll define this function as follows. See, for a fixed S, right, you give S, right, and also I'll write this as phi of, this is basically notation, okay, so don't get confused with the whole thing. Okay, so given a state and a value V, right, phi is this map. Okay, I'll write it in this fashion. You understand what I'm doing here? Is this fine, or is that okay? Suppose you give me a state S and a value, right? Value vector. Phi maps value and states to this number. Okay. Is that okay? Huh?
Yes, sir.
Right. So I can look at this as a map. Okay. So essentially, if you don't worry about the states, in goes the value, out comes some number. That's what phi is. Okay. Yeah. So another way to look at this is, in goes V, the vector. Okay, how many are there? So for each state you have a value. So it's R power cardinality of S, right? In goes this phi, out comes a number, the value, some number. Okay, this is how it looks like. Okay, now I can look at this as a function, right? So give me a value, phi of A will give me a number. Okay, so this leads to, so suppose this function is, let's say, as I mentioned in the previous class, if it is Lipschitz, I can keep on, I'll take V0, take phi of V0, and then take phi of V0, then take phi of V0, and keep on doing that. Hope that it goes to V star. Okay, that's the idea. Okay, so now this leads to an algorithm. We'll prove that this algorithm is good. This leads to an algorithm called value iteration. Okay, so what does it take? So it will take the initial value. So I'll pick some initial vector in R power of dimension mod S, right? That's the vector. I'll feed that as V0 and I'll iterate. So what do I do? So I'll take V0 and substitute it to V, okay? And then I'll do this while, if you look at V, the updated V minus phi of the updated V, whatever norm, I'll talk about the norm a little later. If this is greater than or equal to some threshold, so don't worry about threshold now. Okay, this do, I'll update V as follows. Okay, phi of V. Okay, return phi of V. So this value phi of V will be your V star. Okay, that's the claim. Is the iteration clear? So all that I'm doing is phi V, phi of V, phi of V, phi of V, and so on, right? Or if V0 is the initial value. So essentially we are doing this phi of V0. Okay. Hope that this will be equal to V star. This is hope. Okay, we don't know, right? So let's see whether that is true. Okay, so this is the theorem that shows that this is indeed true. Okay, it says that for any initial value,
Sir, up to what step do we have to do this phi of up to this phi of V star?
this says that, right, while the norm difference is greater than 1 minus nu by nu epsilon, right? You do. So you have to give me what epsilon is. Okay, so given nu is your discount factor. So I know this number. So as long as it's less than or equal to 1 minus nu or nu epsilon, you keep doing this. The moment it exceeds, you stop. Sorry, it's the other way. As long as this difference is greater than or equal to this, you keep on doing this. The moment it becomes lesser, you stop. Okay. So let us look at what are the consequences of that. So if you stop immediately after this difference is less than 1 minus nu or nu epsilon, essentially you will have an accuracy of the order epsilon. Okay, we'll see that will pop out as a consequence of the proof. So take any initial value V0, the sequence. Okay, so if you look at the sequence Vn plus 1, phi of Vn converges to V star. Okay, so let's look at the proof of this. So why is this true? So essentially we have to prove that this phi is Lipschitz continuous. Okay, it's gamma or nu Lipschitz. First step one. So claim, just say first claim, phi is nu Lipschitz. Okay, this is the claim. Okay, so with respect to the infinity norm. Okay, so this is the claim. Okay, so let's look at this. So what do we do? So what is Lipschitz continuous? So Let me just, this is an aside, maybe I'll use a different color. So phi of v minus phi of u, the infinity norm is less than or equal to nu times v minus u. Okay, infinity norm. So this is what you mean by Lipschitz continuity. Okay, you take any two value vectors v and u, phi of v minus phi of u is smaller than v minus u. So if gamma is, let's say, 0.5, right, all that it's saying is, if you look at the y-axis, right, phi of u minus phi of v, that difference is smaller than half of the difference here. So essentially, if I want to write it in terms of a picture, so if you change in the x direction by, let's say, smaller than, this will be smaller than delta by 2. Okay, so a significant change in the x-axis results in a smaller change in the y-axis, smooth, smaller change. Okay, that's what Lipschitz continuity is all about. Any questions so far? Huh?
Hello, sir.
Yes.
So phi is defined as before, right?
Phi is defined here. This phi. Okay, sorry. Yeah, this phi.
This phi, right?
Yeah, this phi. Okay. Okay, so let's look at the proof now. So, of course, this is what you have to do, right? So phi of v of s, you fix an s, okay, state. What I'm going to do is, phi of v is a vector, okay, so for each s you will get, so v of s is a number, right? So phi of v is a vector, so I'll look at the component of v of v. Okay, so now phi of v of s, sorry, u of s.
So isn't it the other way around, like v is a vector and phi of v is a number?
Okay, so let me just clarify that. So what is this? No, I think I did a mistake here. So phi of, sorry, yeah, so I'm sorry about this. So this is, okay, so what I meant here was, for a given s, this is a number. Okay. In goes v, out comes a vector actually, right? So is that clear? Phi of v of s is a number. Is that okay? So that means, to be strictly speaking, it should be r power s, even here. Is that clear? For each s, phi of v of s is a number. So you take different s, you will get different numbers. So basically, phi of v will give me a vector of size s, cardinality of s. Is that okay?
Okay, so it's, like kind of element-wise operation of phi, kind of on.
Yeah, so you can think of this as element wise, right? Phi of this definition, you can think of it as element wise. So if you look at, if you stack all the s's, right? I mean,
Yeah.
v of s, right? You stack all of them, that's a vector. Phi operates on that vector and you get another vector.
Okay, sir. Okay.
Okay. Yeah. Okay. So now let's look at this. So what can you say about this? What is phi of v minus phi of u of s? Okay. Now let me write an inequality and explain why this. So basically, if I say that is the max of the action, so basically, if you look at the definition of phi of s, right? Okay, so let's assume that if you solve this problem, the action that you get is a star of s for a state s. Is that okay? Either is the max action defining p of v of s. Okay, if this is the case, what I can do is I can just say less than or equal to, so I'll just keep phi of v of s as is, minus, I'm just removing the max here, right? Minus max, if you remove max, the negative quantity, that quantity decreases, so the difference increases, right? Minus expected value of, I'll write it like this, expected value of R of S comma A star of S, right? Plus mu times summation over all S dash probability of S dash given S comma A star of S times, see, this is phi of U, right? So you'll have the action U of S dash. Is this okay? Fine.
Yes, sir. Yeah.
Okay. Yeah. Okay. Now I'll write the next step. So you should tell me why. Why is this true? Okay. So now I can write this as new summation for all S dash probability of S dash given S comma A star of S. Okay. Now I'll write this thing as, okay, V of S dash minus V of S. Sorry, not V of S, U of S dash. Okay, is that fine? So why do you think this is true? Why do you think this is true? This comes from the definition, right? Okay.
So we have just expanded phi of V of S, right?
Yeah. So you expand phi of V of S, and then use that here, right? So
Yes.
essentially the difference, right? Now what I can do is I can replace this
Sir,
difference.
phi V of S has a maximum term, no? So maximum over A something.
Correct. So okay, so there is a max, and the max with respect to U of S would be okay. Sorry. Okay, there is one small thing that I have to do, right? Yeah. So I think I didn't highlight this. Okay, let me highlight this. You understood, right? This is with respect to this quantity. Okay, so the action A star of S is the maximizing action with respect to phi of V of S, not phi of U of S. So there is a max over all S, max over all action phi of U of S. In the definition of phi of U of S, there is a max over all action, right? But instead of that maximum action, I'm going to take A star of S. So it won't maximize the term, right? So it will result in a smaller quantity. That's why it results in less than or equal to. Now in the subsequent thing, when you write the definition of phi of V of S, right? What is phi of V of S? Maximize over all action, whatever, blah blah blah. But that action is A star of S, right? So it will be expected value of R of S comma A star of S plus blah whatever gamma into this. So that cancels with this. Is that fine?
Yes, sir. You mean, sir, A star S is you have already assumed is a maximum, no, sir?
Maximum. So they cancel with the corresponding expected value of R comma R of S comma A star of S in the definition of phi of V of S.
Yes,
Okay.
sir. Yeah.
Is it clear?
Yes, sir. Yeah.
So suppose I take the this and replace it with, let's say, max here. Okay. Infinity norm. Okay, the max norm, the sup norm. Then I'm basically replacing this with the maximum possible difference, right? Then of course I should get an upper bound, right? Mu S dash probability of S dash given S comma A star of S times the V minus U. I'm sorry, this is not S star. I don't need this, right? So this is, I can think of it as a vector and look at the infinity norm. Okay, this is infinity norm. Okay, what is this? So V minus U infinity norm doesn't depend on S dash, so I can pull this out of the summation. But if I sum over all S dash, probability of S dash given something, that is 1, right? Because it's a probability. So you'll get Do you agree? Is that fine? Okay.
Yes.
Now interchanging the roles of u and v, we get, see, this was phi of v minus phi of u. Now I can do the same thing with phi of u minus phi of v. So you'll get the same inequality. So therefore, it results in phi of v of s, or in general, I can say phi of v minus phi of u norm. Of course, I'll take the infinity norm is less than or equal to v minus u infinity norm. So that proves the Lipschitz continuity, right, of the function phi. Is that okay?
Yes, sir. Yeah.
Okay. So now, if you look at the Bellman equation, right, now by Bellman equation, okay, I'll point you to the Bellman equation. So what is Bellman equation? This iteration v star equal to, where is that? Yeah, so this is called the Bellman equation. Okay, this equation v star of s equal to max over blah blah blah, and then summation over all s dash p of s dash given as a v star of s dash, right? That's called the Bellman. So Bellman equation says what? So it says phi of v star of s is equal to v star of s, right? Do you agree with this?
Yes, sir.
Yeah, right. So I'll go back. Wait. Yeah, v star is equal to max over all this. This is nothing but phi of v star of s, right? So this gives me a mapping from the mapping phi will map v star to v star, right? So it's a fixed point, right? So v star is a fixed point of phi. Okay. So now we have shown that the function is a contraction, and v star is the fixed point. All that I have to prove is this iteration will lead to v star. That means if you look at v star and you look at, let's say, vn, let's look at vn plus 1. Okay, you know how to do what is vn plus 1 in the algorithm?
Phi of Vn, sir.
Phi of vn, right? So let me write this. This is phi of vn is vn plus 1, right? So now you look at the difference of this. So v star minus vn plus 1. Let's look at infinity now. Okay, so what is this? I can write v star as phi of v star, right? Because it's a fixed point. Vn plus 1 as phi of vn, right? Infinity now. Do you agree? But
Yes,
this
sir.
difference infinity norm. Again, I can do nu square times v star minus vn minus 1 infinity. If you do this enough number of times, you get nu n plus 1, right? V star minus v0 infinity norm. Do you agree?
Yes, sir.
Okay. Now, v star minus v naught infinity norm is some number. Okay, it could be 100, 10, 4, whatever it is. What is nu? This nu belongs to 0, 1, right? It's some number between 0 and 1. So if you take a number between 0 and 1 and raise it to the power, let's say 100 billion, what do you get?
So it will converge to 0.
Yeah, it converges to
0, sir.
0 as n goes to infinity. Is that fine? That means as n goes to infinity, v star minus vn plus 1, the max component of this difference vector goes to 0. That means every other component should also go to 0. That means vn plus 1, every component goes to the components of v star, which is the
Yes. Yes,
optimal. Is that fine?
yes, sir.
So this sort of proves
Here,
the
how we're able to
yes, yes,
hello.
go ahead.
Yes, sir. How
Yes,
we
yes.
are able to go from gamma to gamma square, like from gamma to
Okay,
gamma square?
so
The
okay,
first step here.
let me do this here. V star minus Vn This is what we have. Fine. Is that okay?
Yes, sir.
So I can write this as same step, right? Phi of V star, because phi of V star is equal to V star. But what is Vn? Vn is phi of
N minus 1.
this is what? Nu of V star minus Vn minus 1. Right? Do you agree? Is that
Yes, sir.
so now what do we have here? We have nu times, right? I'll multiply nu everywhere. So nu becomes nu squared here. So when I keep doing this again and again and again, nu squared becomes nu cube, nu power 4, and so on, nu n plus 1. Okay?
Okay, okay.
Is this clear? Yeah. Okay. Okay, now let's prove some optimality guarantees. I mean, if I, of course, it takes infinite steps to go to 0, right? But I'm okay with some solution that is epsilon close to V star. I'll stop there. Okay, that's what practitioners should do, right? You should not keep on iterating forever. So let's look at what is it that you'll get. So for example, V star minus Vn plus 1. Okay, this is what, again, we'll look at infinity norm. Okay, so this I can write it as I'll apply. Okay, I'll ask you what this is. This is phi of Vn plus 1 infinity, okay, plus phi of Vn plus 1 minus Vn plus 1. How do you get this?
Sir, we
Somebody tell
just
me.
plus minus phi of Vn plus 1, then triangle inequality. Sir.
Yeah, triangles inequality, right? I'm adding and subtracting this term here, and then a plus b norm is less than or equal to norm of a plus norm of b, right? That's the triangular inequality. Is that fine, everyone? Is that okay? Okay, so now I
Yes,
can
sir.
write this as phi of v star minus phi of vn plus 1 plus phi of vn plus 1 minus phi of vn, right? Because vn plus 1 is phi of vn, right? Infinity now. But this is less than or equal to mu times v star minus vn plus 1 infinity norm plus mu times vn plus 1 minus vn infinity norm. Okay, fine. Okay, so what if you look at this and the left hand side, they are same. So rearranging terms, we get this implies v star minus vn plus 1 infinity norm is nu less than 1 minus nu vn plus 1 minus vn infinity norm. Okay, okay, so now I want, let's say this is less, okay, sorry, this difference, I want this to be less than or equal to epsilon, right? That's what we want. So essentially v star is epsilon close to vn plus 1, right? That's what we want, right? Do you agree? Okay, so now let's look at this term. So essentially let's also look at this vn plus 1 minus vn infinity norm, that's equal to, again, phi of vn minus phi of vn minus 1 infinity norm, that's less than or equal to nu times vn minus vn plus 1 minus 1 infinity norm. And if you keep on doing that, you'll get this, right? Nu power n vn will become phi of v0, right, minus v0 infinity norm, right? So essentially vn plus 1 minus vn infinity norm is further bounded by nu n times this difference, right? So now basically I want this to be less than or equal to epsilon, right? So want the above to be what? Some 1 minus nu or nu epsilon, right? That's what we want. Do you agree? above to be less than or equal to 1 minus nu or nu epsilon, right? Do you agree? Is that fine? Okay. So this implies 1 minus nu or nu epsilon is less than or equal to gamma power n phi of v naught minus v naught infinity norm, right? So this implies I'll do the rearrangement. Okay, so it's gamma n, right? Gamma n is greater than or equal to 1 minus nu or nu epsilon times 1 by p of v naught minus v naught infinity norm. Is that fine? So I'll
Yes, sir.
take logarithm on both sides. N log nu is greater than or equal to log of, okay, I'll write it like this, 1 minus nu over nu plus log of epsilon, okay, plus log of, well, this is minus, right, minus log of p of v naught minus v naught infinity norm. Okay, this is what you get. But yeah, so if you look at this, what can you say about log of nu? I can write log of nu as 1 by nu, but with a negative sign. Do you agree? Do you agree? Yeah? Is
Yes,
that
sir.
fine?
Yeah.
Yeah. But nu is less than 1. Therefore, 1 by nu is greater than 1. Therefore, log of 1 by nu is positive, right? This is greater than 0. Right? So, if I multiply minus n on both sides, what do you get? N, right, is less than or equal to, basically you have log nu and all that, right? So if you don't worry about these terms, right, so this log news and these terms, for example, right, so it only depends on, well, I have to multiply by minus on both sides, so log epsilon becomes log 1 by epsilon. Okay, so now the only parameter that I'm interested in epsilon, so I'm going to make epsilon smaller and smaller and see how n changes only with respect to epsilon. I don't care about the other term, right? So it will be the order of log of 1 by epsilon. Okay, that means if you repeat this algorithm value iteration n number of times, where n is order of log of 1 by epsilon, the solution that you get will be epsilon close to the optimum. That's what it's saying. Is that fine? The exact difference is this: you should find an n that satisfies this equation, right? This inequality. Is that fine, everyone? Is that okay?
Yes,
Hmm?
Yes, sir.
yes, sir.
Okay, so the next thing is what is known as policy iteration. So there are two things, right? Value iteration will give you the solution, but if you want to do value iteration, you have to do phi of v0, phi of v0, and so on, right? You have to operate phi. What is phi? You are maximizing over some function which involves conditional probabilities, right? P of s dash given s comma a. But that is something that you don't know, and therefore you cannot do that value iteration, right? That's the problem. Do you agree with this? Okay, so of course, assuming that you know the transition probabilities, you can do this. The second thing that we are going to do is called the policy iteration. So I'll just write this. Okay, again, the policy iteration, you iterate over policies, not over values. Okay, so policy is pi, right? So pi 0 is your initial vector, the policy. I'll do this. Okay, and then while whatever pi, okay, I'll just I'll leave it, so let's write it later. So what you do is you initialize value to v pi. Okay, so how do you get v pi? Solve the value iteration. So 1 minus nu p pi times v is equal to r pi. So this is something that we know we have a solution, right? From this you can solve for v, but that v depends on pi. So let me call this as v pi. Okay, and change my v to v pi. Okay, and now I'll update my variable pi dash to pi. Okay, so whatever pi that I have policy, I'll update. Now this is the basically think of it as a temporary variable where you are remembering what was the previous policy. Now you have to update the policy. The way you are going to update is you will pick a pi that maximizes the following. Okay, so r pi plus mu times p pi times v, right? You have the value, right, the previous value, and find the argmax and look at this. Okay, and return, well, keep doing that, return pi. But when should you repeat? As long as pi is not equal to pi dash, repeat it. Or if you want to change this, you can say, well, policy pi is close to pi dash in some norm. You keep doing that as long as it's less smaller. The difference is small, you stop. Otherwise, as long as the difference is large, more than some threshold, you keep doing this. Okay, so this step is called greedy step because for a given value and pi, given value and p pi and r pi, you're trying to optimize your policy pi. So you're greedily choosing pi. Okay, so now this is called the policy iteration. You're choosing your policy based on this equation. So it turns out that this policy iteration converges faster than the value iteration. Again, we have the same problem in general unknown. Okay, this in general unknown. Okay, so the next question after addressing this would be, what if you don't know this p pi? How do you modify this? That leads to some other algorithms that we will look at later on. Okay, so maybe in the next class we will look at the proof of this and then convergence proof of this, and then we will look at what if we don't know p pi. That leads to q learning and td lambda, all the temporal difference or temporal difference algorithms. Okay, any questions? Yes,
Sir, pi not equals to pi dash means what does it mean, sir? Means actions. No?
pi is a policy, right? What do you mean by policy? It's a map from state to action.
Function.
Yeah, it's a function. Whenever the function pi is not equal to the function pi dash, you do. That's what it means. So oftentimes if this, see, okay, let me put it like this. If your state is, let's say, you are in good state or bad state, okay, these two states, and your action is transmit, not transmit. This is your policy. Okay. How many such policies are possible? 4 policies are possible, right? What are those 4 policies? You map everything to 0, you map everything to 1, you map 0 to 0 and you map 1 to 1, or you map 0 to 1 and you map 1 to 0, right? These are the 4 possible policies. Do you agree? You keep on iterating. Yes. At some point the policy won't change. It says map 0 to 0 and 1 to 1. It will keep on doing that. Then you stop. Okay. Is that fine? If it is not discrete and you have continuous and all that, then you cannot do this, right? So pi will never be equal to pi dash. In that case, we may have to look at some norms and all that. But for discrete case, this seems reasonable. Is that okay?
Yes, sir.
Okay. Yeah, good. Yeah, any other question? Mandeep, you have any question? So this is the policy iteration.
No, sir.
Okay. So you understand the issue, right? So if you don't know, for example, the transition probability matrix for each pi, then you cannot do any of these. But when you do research, right? For example, let's say in the 1950s, people started looking at this and then they wanted to solve this. First thing they do is let's assume p pi and see whether we can solve. If we can solve assuming p pi, then we can hope to solve problems without knowing p pi, right? That's the natural approach. They said, well, let's assume p pi and see what is it that I get. They got these two algorithms. Then they said, well, now let's attempt the case where we don't know this. That led to a series of other algorithms. Okay, is that fine? Okay, any questions?
Sir,
Yes.
sir, can you, update this PDF or this note, this class note?
Update
mean,
me.
Can you share this notepad for this class?
Huh.
I
So
mean,
what
will
I
we-
can do is I can point you to the right. Okay, I can share the notes. No problem.
Okay.
Okay. Okay,
So
I'll
can you
share
share
it
some
later.
resources also?
Yeah. So I'll do that. Maybe I'll do that itself. So I'll share the resource rather than the notes. You can go through the resource. Right, Rishabh? So it's a book by Mohari. It's a chapter on reinforcement learning. The title of the book is, I think, Foundations of Machine Learning. Okay, it's available online. Do we have Savan is there? Okay, he's not there. Okay, I'll point you to the link, huh? The paper, the book. It's available online, I think. Okay, Rishabh.
Okay,
Any
sir.
questions, Rishabh, Praveen, Ayush? Ayush, do you have any questions?
No, sir.
No. Sumit?
No, sir.
No. Okay.
Sir, this policy iteration, sir.
Mm-hmm.
So in policy iteration, actually, sir, there are so many policies. Suppose we are taking the states, the countable states. So are we doing on finite state or we can take the countable states, sir?
You can take countable states, but whatever we did until now is for finite states. I don't think it will. I don't know if there are no issues. I mean, you can still do countable. I don't see any issues. I'll have to see through the proof.
Countable, no, sir.
Huh?
Then, sir, if we take the countable number of states, then, sir, the number of the policies will be uncountable, sir, I think.
Correct.
Yeah,
Correct.
it's uncountable number of policies are there. So in that
Correct.
case, sir, iterating the thing, like from where to start and how to iterate, like in the sir value iteration, sir, we just
I
take
understand.
any fixed point, start with any v naught, no, sir,
Yeah.
and then we are just keep on iterating and we converge to the some point. But
Correct.
sir, here I think it will not go like that on, sir.
True. So when you have, for example, uncountable actions, right? Then I think still you can manage in the sense you cannot use, for example, certain proofs don't work. And I think let's look at the algorithm. Maybe I'll look at where is that? See, value iteration, right?
Yes.
There is, as long as you can compute this, I don't care. Do you agree?
Yes, sir. Yeah.
Yeah. So you keep iterating until convergence. Do you agree?
Yes, sir.
But the only thing is this V as a function of, I mean, if you look at the states as countable but infinite, then you have infinite thing, right? But for all practical purposes, you can assume that it's finite. I can, even if it is infinite, I can approximate it by a finite quantity, maybe huge. So that's the issue. Okay. So in all of these problems, if the states are like huge state space, let's say you have a billion state variables, then you have a billion by one vector. Very hard to you can still do value iteration, but again there are issues there. Value iteration you can do, but you don't know p pi in practice, right? There are issues there. I mean, when you do, when you look at such problems.
So like the value iteration, we just defined a function and we already showed that the Lipschitz function. So then it will guarantee that it will converge to that point only. But sir, in the policy iteration, we don't have any such a thing. Like,
No. We will prove that this indeed converges.
oh, okay, sir.
Yeah, we will prove
Sir,
that.
how we can say that policy iteration will converge faster than value iteration?
We will look at the proof in the next class. Okay.
Okay. Okay.
So essentially, what you do is each iteration, you show that the policy iteration achieves a better value than value iteration. Okay. For example, value iteration, if you call, let's say, some Vn, let's say policy iteration is Vn. Okay. Value iteration is Un. So you show that Vn is greater than or equal to Un for every n. Okay. What does that mean?
Okay, sir.
Vn is approaching, that is policy iteration updates are approaching V star faster than Un, right? Which is the value iteration. That's the idea. Okay.
Okay, sir.
Yeah. Okay. I'll stop here, and if there are no questions, we'll come back in the next class. So I'll try to conclude in the next class, but if not, maybe one or two more classes. That's all. Okay. Yeah.
Okay, sir.
Thanks. Thank you.
Thank you, sir.
Yeah.
Okay.
Bye.
Sir,
Yeah.
so, I mean, sir, I will request you again to, to share these class notes and the previous class notes. I mean, it will be easy to connect. I mean, the material also will help, but the notes will.
Yeah, I'll send it. We have PhD interviews going on, so that
okay,
over. I'll send it to you today, huh?
Sir, no problem. No. Okay,
Okay,
sure.
thanks. Bye.
Thanks.